Hello and welcome to day 6 of learning ML from chatgpt. So let's get started. So as a recap, yesterday we did logistic regression and we used the softmax function in order to train our model on the MNIST dataset, which is a bunch of handwritten numbers, just digits, 1 to 9, 0 to 9 rather. So here we just train the data. No, sorry, we didn't train data. We got the data from the MNIST dataset, and then we converted it into the correct format, which was like 700 something, because this was the size of the image, so that the computer could understand it better. Then we had the Keras model with a dense layer, and this was the activation function softmax, which splits, you have basically. So for 0, you would have a percentage prediction, and 0 all the way through to 9 we have percentage prediction. This would be from the softmax function, and the highest, the one with the highest probability of it actually being predicted by the model is the one we use. We saw that ours had like a 91.5% accuracy, but then when we fine-tuned the hyperparameters, we can see it got marginally better, like by 1% or something. Just under 1%. I think it was 92.33. So then we fit the model and validating data, and then we print the accuracy. So now let's copy paste the day. So it's day 6. Performance metrics. We'll see what this is going to be about. Okay, so please give me day 7's lesson. Okay, so performance metrics. Concepts: accuracy, precision, recall, F1 score, confusion matrix, code examples, calculating performance metrics using scikit-learn, assignment, evaluate the performance of your logistic regression model. Overfitting and regularization. Concepts: understanding overfitting and underfitting, introduction to regularization techniques, L1 and L2 regularization, and dropout, how to apply regularization in TensorFlow and PyTorch. Oh yeah, I forgot to ask it to only do TensorFlow today. I'll try and remember for tomorrow. Code examples: implementing L2 regularization, ridge regression in TensorFlow and PyTorch, adding dropout layers in a neural network model. So assignment: train a neural network on a dataset with and without regularization and compare the performance. Plot the training and validation loss to observe overfitting. So overfitting. A model is overfitting when it performs well on the training data, but poorly on unseen data, test set. Okay, so it's overfitting. It means the model has learned the noise and details in the training data to the extent that negatively impacts the model's performance on new data. Underfitting occurs when the model is too simple to capture the underlying pattern of the data, leading to poor performance on both training and test data. So that's underfitting. So overfitting, which is one in training, but we don't want overfitting or underfitting because they both don't give us the results we want. So regularization techniques. Regularization techniques help reduce overfitting by discouraging the model from fitting too closely to the training data. L1 regularization, lasso, adds a penalty equal to the absolute value of the magnitude of coefficients. Okay. L2 regularization, ridge, adds a penalty to the square of the magnitude of coefficients. Dropout, a technique where randomly selected neurons are ignored during training. This forces the network to learn more robust features that are not reliant on specific neurons. Code examples: regularization in TensorFlow and PyTorch. Regularization in TensorFlow. Okay, so we're having 2 dense layers, one with activation of ReLU, another one. So this is still, I guess, the MNIST dataset. So softmax activation again, as compared to what we had before, and it's 10 because we have 0 to 9. as our output. Then we're compiling the model as the optimizers Adam, categorical cross-entropy as we saw yesterday, and metrics accuracy. So history model will fit, and we're passing in 10 epochs and batch size again. Then the validation data is just very similar to what we saw before. Then we're printing the accuracy. So let's see what we're using here. Load data. So this is the, I assume this is the ReLU is the kernel regularizer. Well, oh, okay, so this is it. Adds L2 regularization to the dense layer. Regularization strength 0.001 controls the amount of penalty applied to the weights. Okay, dropout in TensorFlow. So dense, dropout 0.5. And we're just compiling the model and fitting it like we did before. Dropout during each training step. 50% of the neurons in this letter we randomly ignored. Okay. And we're also having the activation softmax. So the only thing we're changing between these two is the kernel regularizer L2. So this is just regularization. And this one we just add dropout in order to make our model not too dependent in each specific neuron and like make it learn, like basically make it do it like the hard way, not just rely on the training data. L2, okay, I'll skip this as we're just going to carry on with TensorFlow. So training neural network on an MNIST, then with, okay, so what I'm going to do is, so I'm just going to copy both code snippets from the TensorFlow one and this one, and we'll compare the differences in the performance of these models. I just want to check, did we have the ReLU activation yesterday? No. Okay, so we just had this. So we're having an extra layer here. Is this? Okay, it's just importing. So I'm just going to reread this again. I'm going to ask you to explain. Please explain this in simple terms. Let's break it down. L1, regularization, lasso. What it does. L1 regularization adds a penalty to the model based on the absolute value of the weights in your model. Why it's useful. This penalty encourages the model to keep the weights small. In fact, it can even force some weights to be exactly zero, effectively removing those features from the model. This makes L1 regularization useful when you want to create a simpler model by automatically selecting only the most important features. Okay. L2 regularization adds a penalty to the model based on the square of the weights in your model. This penalty also encourages the model to keep weights small, but unlike L1, L2 regularization tends to shrink the weights towards zero without making them exactly zero. This makes L2 regularization good for when you want to prevent the model from giving too much importance to any single feature, helping smooth out the model's predictions. Okay. L1 simplifies the model by making some of the weights. So, my take on this is that L1 regularization. So this one, we want to make our model simpler because we want to eradicate some of the features in our pandas data frame, for example. so that like the relevant ones are not used. Whereas L2 regularization is just like it uses all features but doesn't like become over reliant on a particular feature. So this means that it won't do overfitting or underfitting. It will just be, it won't be too dependent on each one. So yeah. So it prevents any single feature from dominating the model by making your weight smaller, but not exactly zero. Okay. I'm going to see if this is run now. Still. How? Everyone needs to just keep on the tab. Or I've run out of Google Cloud storage, which is a possibility. So I'm 24. How do you get lines on? What are we doing? Error handler. Maybe it's 0.001 to... I'm going to go back to chatgpt and see what it said about this. L2 regularization. Regularization strength 0.1. And the amount of penalty applied to the weights. Okay. So L2 is the one where it's squared. We're not using L1 in this particular format. I'm just going to go back to the dropout technique where random selecting errors are ignored during training. Forces the network to learn more about robust features that are not reliant on specific neurons. Okay. So we're like not training our model on a thing that's like that's being trained on. It's being trained, but it's making the wrong assumptions about the data. I see. So then it can't be carried forward to other data sets. Looks to finish 3 minutes. Okay, so 95.68%. That was a great increase from yesterday. Wow. And that's all when we just added this extra kernel regularizer L2. Okay. Okay, this is going to take a while. I'm going to reread through our lesson. Regularization techniques to help reduce from fitting too closely to the training data. A penalty equal to the absolute value of the weights. As a penalty equal to the square of the weights. Okay, so well, first of all, I'm going to make an assumption about this. I assume that L2 regularization is going to have a better performance than the just like dropping out as so dropout technique randomly. I need to ask it to explain. Please explain L1 and L2 in more detail. I get that they are to reduce overfitting and underfitting, and that they are basically punishing the model into not being too reliant / fixated on the training data. Is my understanding correct, or are there or is it different? Please give the explanation. Okay. Your understanding is on the right track, but let's dive deeper and clarify the expanding concept. So overfitting happens when a model learns. So just from memory, so overfitting, it learns the training, but it can't do well on the actual data. But also noise and outliers. This leads to excellent performance on training data, but poor performance on unseen data because the model has become too fixated on the specifics of the training data. Rules of regularization. So regularization techniques such as L1 and L2 are tools to prevent overfitting by adding a penalty to the model of having large weights. Okay. The penalty discourages the model from becoming too complex and over-reliant on any specific feature, thereby helping it generalize better to new data. Okay. So the weights, yeah, they're just each feature I assume then has a weight, and the bigger weight it has is the more influence it has over the output. Okay. So the penalty discourages the model from being too complex and over-reliant. Okay. So the penalty is just gives. So we had the 0.001 as the penalty. Then yeah, that's the penalty. How it works. L1 regularization as a penalty to the loss function equal to the absolute value of the weights. Here, W1 represents each weight in the model, and lambda is W sub I represents each weight, and lambda is a hyperparameter that controls the strength of regularization, how much penalty is applied. Effect on the model. Sparse models. Regularizations tend to push some weights to be exactly zero, effectively turning off some features. This results in a sparse model, meaning only the most important features are kept, the rest are ignored. Feature selection. This makes L1 useful when you want the model to automatically select a subset of features that are most relevant for making predictions. Intuition. By penalizing the absolute value of weights, L1 regularization forces the model to prioritize features, keeping only those that have strong direct relationship with the target variable. Okay. How it works. L2 regularization. Ridge. And the other one is lasso. Okay. Adds a penalty to the loss function equal to the square of the weights. Weight shrinkage. L2 regularization intends to reduce the size of all weights, but it doesn't usually make them exactly zero. Instead, it shrinks them proportionally, which keeps all features in the model, but at reduced influence. Smoother models. It helps in creating a smoother, more generalized model that doesn't rely too heavily on a single feature or small subset of features. Intuition. By penalizing the square of the weights, L2 regularization discourages the model from making any feature overly important, leading to a more balanced and stable model. So the differences, so this is important. These are sparse models. Many weights are exactly zero, can be used for feature selection. Okay, that's definitely a benefit. When maybe you've got thousands of features and it's just really hard to it's easy if you have it just for 10. You could see and make reasonable judgments. For example, I was doing a course where there was one about taxis, and I think it was the weather, so it didn't have an effect on the tip. Maybe not being weather, but So L2 regularization. These are small, non-zero weights for all features. Does not inherently select features, but balances the model's complexity. Why regularization reduces overfitting? Both L1 and L2 regularization reduce overfitting by discouraging the model from becoming too complex. Complex models can fit the training data very well, even memorize noise, but they perform poorly on new data as they don't generalize very well. Regularization keeps the model simpler by constraining the size of the weights, making it less likely to memorize the training data and more likely to capture the true underlying patterns. Conclusion. Regularization is about finding the right balance, a model that's complex enough to capture the important patterns in the data, but simple enough to generalize well to new unseen data. L1 and L2 regularization are powerful tools to help achieve that balance, each with its own unique impact on the model. Okay, now this should have been finished. And mode achieved. Wow, 98.21%. That's huge. I didn't actually expect that. Wow, okay. How long did that take? I'm assuming around the same time. Oh, 2 minutes, even quicker. Wow, that's amazing. 98.21%. So now that we've compared them, what training and validation last week, please. Observe and explain the impact of regularization on overfitting. Okay, I don't know how to plot it as I'm not too familiar with Matplotlib, but I'll try and explain it. So L2 here, this is when we use the square of the absolute weight, and here the penalty is 0.001. So we don't want the model to be too complex here, so we just give it a penalty and make sure the weights for each feature are not too high, so it's not too complex of a model. And the square ensures, well, almost all of the time, it won't be zero. So no feature will have too high of a weight, and therefore it'll be not evenly distributed, but every feature will have at least a bit of a say in the model. We're doing this because we don't want the model to be trained on noise that's present in the training data, which will not therefore be able to use in other unseen data. And then here in the dropout, we're just randomly dropping out half of the data, and then that ensures that there's not any patterns between the noise, which won't be present in other data sets. So we can just remove that, the worry of it being trained on just the training model's noise. Okay, but I'm really surprised that it's gone all the way up to 98.21%. I mean, that's amazing. Okay, so I'm just going to ask it like I did yesterday. So now please write a snippet of code that outputs a random like, what do I call it, an image from the test dataset and prints the prediction and the actual value. Wow, they are hugely powerful L1 and L2 regularization though. I mean, hats off to them. As is the dropout. Like, how much percent increase? I can't remember the first one. Yeah, that's like 4% increase. Just under 4% increase. That's huge. Okay, I'm just going to copy this again. Hopefully it won't take too long. While we compile it again though, I'm just going to copy this instead. Because I assume we've got all of this. Well, this one... I'm just going to copy this and see if it does work. I need to import Matplotlib. Oh, it's just printing 0, 1, 2, 3, 4. So this is the output we get. We're printing actual label. No, actual random label. So y test at random index. Okay. So this is the that's the shape of it, the 10, because we're doing 4. Yes, okay. Run this again. 9. What's it? Oh, I think of that as a 4. So even the model with it. 2, 0, 4, 1. Yeah, you can see with this, it's extremely accurate. And this is, yeah, this is true. I'm just going to read through what this does. So we get a random index. We did this yesterday, we're just recapping. And x random image equals s test dot reshape 28 by 28. So we originally had it as 7. We converted it into the 720 whatever it was shape, that because that's what we needed in order for the model to be trained. And then we're having a random label y test dot random index. Then we're reshaping it again, the image and prediction, image flat, and predicted label equals, and then we're just getting the prediction as the using numpy's argmax function, and we're showing it. Okay, so random index. Okay, so yeah, that's it. And this is super powerful model, as you can see, with a 98.21% accuracy. Yeah, so I'm just going to read the closing notes of the lesson. So, concepts covered: overfitting, underfitting, regularization techniques L1, L2 dropout, skills developed applying regularization to neural networks using TensorFlow and PyTorch, assignment, experiment with different regularization techniques to prevent overfitting and improve model generalization. Regularization is a crucial concept in machine learning that helps prevent overfitting, ensuring that your model performs well on unseen data. By understanding and applying these techniques, you'll be better equipped to build robust models. Okay, so that's all for today's video, so thank you for watching, and I'll see you in the next video. Goodbye.